A silent dance of giants is constantly reshaping the cosmos. Entire galaxies, each holding billions of suns, are slowly colliding and merging across the eons. This is not destruction. It is the primary creative force in the universe. Galactic collisions are the master architects, forging everything from the elegant spiral arms of the Milky Way to the colossal elliptical giants that dominate galaxy clusters. By the end of this journey, you will see the night sky not as a static picture, but as a living, evolving structure built by these immense encounters. We will uncover how a gentle gravitational tug can birth a spiral galaxy, and why our own cosmic home is on an unavoidable collision course. What do you believe is the most beautiful structure in our universe? The cosmos did not begin with its grand designs already in place. It started as a nearly featureless expanse, a cosmic canvas painted with only the faintest of brushstrokes. After the Big Bang, the universe was a dark, expanding sea of primordial gas and an invisible substance we call dark matter. It was almost perfectly smooth, but not quite. Scattered throughout this void were minuscule ripples, tiny pockets where the density was ever so slightly higher than the surrounding area. These imperfections, these seeds of future structure, were imprinted upon the fabric of reality in the universe's first moments. They were the only blueprint available. For hundreds of millions of years, gravity was the only sculptor at work, a patient and relentless force. It tugged at those slight over-densities, causing them to slowly collapse inward, drawing in more gas and dark matter from their surroundings. From this gradual accumulation, the first proto-galaxies were born. These were not the majestic spirals we see today. They were small, chaotic clouds of stars, the foundational building blocks of everything to come. This pristine, almost simple beginning makes the universe's subsequent complexity truly breathtaking. How could such a uniform start give rise to the intricate galactic cities we observe? The answer lies in what happened next as these infant structures began to interact, setting the stage for the first cosmic collisions. Gravity is the universe's great choreographer. It is not merely a force but a master artist's tool, etching the grand architecture of the cosmos over spans of time that dwarf human history. This invisible sculptor begins its work with immense patience, orchestrating a slow dance between islands of stars separated by millions of light years. A single galaxy, minding its own business, feels a faint, persistent tug from a distant neighbor. This is the first step in a gravitational courtship that can last for billions of years, slowly drawing the two giants from the cosmic darkness into an inevitable, graceful embrace. The physicist John Wheeler captured this profound relationship beautifully, stating that space-time tells matter how to move, and matter tells space-time how to curve. This elegant feedback loop is the engine of every galactic merger. The framework for this entire dance is built by the hidden hand of dark matter. Every galaxy is cocooned within an enormous, invisible halo of this mysterious substance, whose gravity provides the primary structure. It is this dark matter scaffold that first reaches out and intertwines with another, setting the stage for the more visible drama to unfold. As galaxies draw nearer, their gravitational fields warp space itself, creating tidal forces that stretch and pull them out of their familiar shapes. Gas and stars are not mere passengers, they are the clay that responds to these forces, flowing and compressing in ways that lead to spectacular new forms. Without gravity's universal and persistent influence, galaxies would remain forever isolated. The cosmos would be a collection of lonely islands, a quiet and unchanging sea of darkness. It is gravity that weaves the rich tapestry we see, pulling these islands together to build the great galactic cities and colossal structures that define our universe. This foundational process sets the stage for the specific, breathtaking types of collisions we are about to witness. The scale of a cosmic collision dictates its final masterpiece. When two galaxies of nearly equal size meet, it is a true clash of titans, a major merger that reshapes the very identity of both participants. This is not a gentle dance but a profound and turbulent rearrangement, where gravitational forces violently tear apart their beautiful spiral arms and scatter billions of stars. The original structures are completely erased, their stars flung into chaotic new orbits. What emerges from this chaos after hundreds of millions of years is often an entirely new class of galaxy, a smooth, featureless elliptical giant. This is cosmic revolution, a violent rebirth that forges the universe's most massive islands of stars. Yet, most galactic encounters are far more one-sided. In a minor merger, a vast spiral galaxy like our Milky Way calmly consumes a much smaller dwarf galaxy, a mere hundredth of its size. This is not a revolution but a steady, ongoing evolution. The larger galaxy's structure remains largely intact, gently absorbing the smaller one's stars and gas, growing steadily larger over time through a process of cosmic accretion. Think of it as a giant city annexing a small suburban town, its skyline changing subtly but not fundamentally transforming. This crucial distinction helps astronomers predict the fate of galaxies. Is a galaxy destined for a dramatic rebirth or a path of quiet, steady growth? The answer lies in the size of its next cosmic partner, a simple ratio that determines whether it will be reforged or simply refined. This understanding brings us to one of the most beautiful outcomes of these gentle, minor mergers, the birth of a spiral galaxy's iconic arms. The graceful spiral arms of a galaxy are cosmic traffic jams. Stars and vast clouds of gas do not remain fixed within these luminous structures. Instead, they orbit the galactic center, continuously flowing into and out of the arms, which are themselves patterns of compressed material moving through the disk. This beautiful paradox is the result of a delicate gravitational nudge. When a small satellite galaxy glides past a larger spiral, its gravity sends a ripple through the larger galaxy's disk, much like a stone creating waves on the surface of a pond. This ripple is a density wave, a region where the galactic material is temporarily squeezed together. As stars and gas enter this wave, their orbits are compressed, slowing their passage and causing a brilliant pile-up. The gas, in particular, is compressed so dramatically that it collapses under its own gravity, igniting the furious birth of new, massive stars. These brilliant, short-lived stars act like cosmic streetlights, illuminating the spiral arms and making the grand design visible across the vastness of space. This process reveals that the most iconic features of our universe are not permanent sculptures but dynamic, living patterns, sustained by gentle interactions. It is a profound demonstration of cosmic order emerging from a subtle disturbance, a testament to how a passing encounter can paint a masterpiece across the heavens. Yet this delicate balance of creation stands in stark contrast to the outcomes of a more violent merger, where the spiral itself is the first thing to be erased. Our own galactic home is a cosmic predator in slow motion. The Milky Way is not a static island, it is a dynamic system actively consuming smaller neighbors. We can witness this process firsthand in the ongoing destruction of the Sagittarius dwarf spheroidal galaxy. Our galaxy's immense gravity has already stretched this satellite into a vast, shimmering river of stars that wraps around the entire sky. This stellar stream is a fossil record of a collision happening in real time, a visible scar from a minor merger that began billions of years ago and continues today. Over the eons, the Milky Way's tidal forces will completely shred this dwarf galaxy, scattering its stars until they are seamlessly mixed into the diffuse halo of our own. This is not a rare event, it is the standard mechanism for how large galaxies like ours grow. They engage in a form of galactic cannibalism, steadily accreting mass by consuming smaller systems. This process of hierarchical growth, where large structures build up from the merging of smaller ones, is a cornerstone of our understanding of the cosmos. It is a fundamental prediction of the leading model of the universe's structure. This gentle, steady diet of dwarf galaxies allows majestic spirals to grow their stellar halos and increase their mass without the violent disruption of a major merger. It is a path of quiet, incremental evolution that has shaped our galaxy over billions of years. Yet this peaceful growth is only a temporary state, a calm before a much more dramatic encounter that will ultimately redefine our place in the cosmos. Every majestic galaxy we see is merely the visible tip of a much larger, hidden structure. The true framework of the cosmos is built from dark matter, an invisible substance whose gravitational pull is the universe's essential glue. During a galactic collision, the most dramatic interactions occur not between the brilliant stars, but between these vast, interpenetrating halos of dark matter. Unlike clouds of gas that can collide and compress, or stars that almost never touch, dark matter particles pass right through one another. They feel no friction, experiencing only the silent, persistent tug of gravity. This means the dark matter halos act as the primary architects of the merger, their immense collective gravity dictating the entire dance. They set the orbital rhythm, determine the final timing, and sculpt the ultimate shape of the newly formed galaxy. Advanced computer simulations reveal a startling truth. If you were to remove the dark matter from a galactic collision, the entire system would simply fly apart. The stars and gas, lacking the binding gravitational scaffold, would drift into the void like leaves scattered by the wind. This is why astronomers study the aftermath of these immense collisions so carefully. The final structure of a merger remnant, the specific way its stars are arranged, is a cosmic fingerprint. It encodes vital information about the amount and the properties of the very dark matter that orchestrated the event. By observing these grandest of cosmic constructions, we are not just learning about galaxies. We are using them as giant laboratories to decipher the nature of the mysterious, invisible substance that shapes our universe from the shadows. These long, graceful arcs of stars are the universe's own forensic evidence. When galaxies interact, they leave behind cosmic fingerprints in the form of tidal tails and bridges, magnificent structures of stolen starlight flung deep into the void. Their creation is a direct result of gravity's uneven grip. Picture our own ocean tides, where the moon's pull raises a bulge of water on the near side of Earth. A similar but vastly more powerful effect occurs during a galactic flyby. The stars and gas on the side of a galaxy closest to its passing partner feel a much stronger gravitational tug than those on the far side. This extreme difference literally stretches the galaxy, pulling its outer layers away and flinging them into space to form these brilliant, ephemeral streamers. In a stunning pair of galaxies known as the Antennae, we see this process in its most iconic form. Two spiral galaxies have recently crossed paths, and their gravitational interaction has drawn out two long, curving tails of stars that resemble an insect's delicate antennae. These are not physical arms connecting the galaxies, but rather separate rivers of stars, each one tracing the gravitational history of the encounter. For astronomers, these structures are a goldmine of information. By studying the exact shape and composition of a tidal tail, they can work backwards, calculating the masses of the galaxies involved and even determining the angle and timing of their initial pass. They are a temporary monument to a specific moment in cosmic time, a beautiful but fleeting signature that will eventually fade as the galaxies complete their final, violent dance. Deep within the swirling chaos of colliding galaxies, a far more intimate drama unfolds. At the heart of each spiral or elliptical galaxy lies a supermassive black hole, a gravitational singularity containing the mass of millions or even billions of suns. When their host galaxies merge, these cosmic monsters are thrown into a fateful dance. Initially, they are carried along with the general flow of stars and gas towards the new galactic center. A process called dynamical friction then takes over, where the black holes plow through the dense sea of surrounding stars. Each stellar encounter transfers a tiny amount of momentum, acting like a cosmic brake that steadily drags the black holes inward from thousands of light-years apart to within a single light-year. This is the first step in a gravitational courtship that will last for eons. As the black holes close in, they become gravitationally bound, forming a binary pair locked in a tight orbital embrace. They whirl around their common center of mass, separated by a distance that is a mere fraction of a light-year. For a long time, this is where the dance could stall. The black holes need to lose even more orbital energy to spiral the final, critical distance toward a final merger. In the final stages, a phenomenon predicted by Einstein over a century ago takes command: gravitational waves. As the two massive objects accelerate in their tight orbit, they ripple the very fabric of spacetime itself, sending out waves that carry energy away from the system. This loss of energy causes their orbits to decay, drawing them inexorably closer in a tightening spiral that culminates in a final, violent coalescence. The moment of merger is one of the most energetic events in the universe since the Big Bang. In a fraction of a second, the two black holes become one, releasing a phenomenal burst of gravitational wave energy. This cosmic shout ripples across the cosmos, a signal that future observatories like the planned Laser Interferometer Space Antenna, or LISA, are designed to detect. The result is a single, even more supermassive black hole, now sitting at the very center of the newly forged galaxy. But the impact of this merger extends far beyond the creation of a more massive singularity. The event can violently shake the entire galactic core, funneling vast reservoirs of gas toward the new central engine or, conversely, flushing it out. This fundamentally alters the energy output and structure of the galactic heart, determining whether it will blaze as a brilliant quasar or settle into a quiet, dormant state. The legacy of the black hole merger is permanently imprinted upon the galaxy it now governs, a final, defining signature of the cosmic collision that created it. The calm, steady rhythm of starbirth is completely shattered during a galactic collision. What was once a gentle process becomes a cosmic firestorm, a starburst that forges millions of new suns in a breathtakingly short period. This transformation is driven by a simple, violent act: compression. In a solitary spiral galaxy, vast clouds of interstellar gas drift peacefully, too diffuse to collapse. But when two galaxies intertwine, their gravitational dance sends powerful shock waves through these gas reservoirs. It is as if a silent, empty concert hall is suddenly flooded with a deafening symphony of pressure. These immense forces squeeze the gas, pushing it past a critical threshold where its own gravity takes over. The clouds fragment and collapse inward, each pocket of dense gas heating up until nuclear fusion ignites at its core and a new star is born. This is not the isolated spark of a single star, but a coordinated blaze, a fireworks display on a galactic scale. We see this brilliant spectacle playing out in the Antennae galaxies, a pair of spirals caught in a close embrace. There, the most intense regions of this starburst activity glow with a distinct pinkish hue. That color comes from ionized hydrogen, a telltale sign of massive, newborn stars whose intense ultraviolet radiation is energizing the surrounding gas. These brilliant nebulae are not just beautiful, they are the factories of cosmic construction, operating at a frenzied, unsustainable pace. This explosive period of creation comes at a great cost. A galaxy's gas is its raw material for future stars, and a starburst consumes this fuel in a blaze of glory. The very event that triggers such prolific star formation effectively burns through the galaxy's primary resource, leaving it gas-poor and quiescent. This is a pivotal moment in a galaxy's life story, a dramatic climax that fundamentally alters its future. The gas-rich, star-forming spiral is, through this violent burst of creativity, being transformed into something entirely new, a quiet, red and gold elliptical galaxy where few new stars will ever shine again. This final, chaotic act of a galactic collision leaves behind a completely new cosmic entity. The elegant, spinning disks of the original spiral galaxies are gone, erased by the gravitational turmoil. Within the swirling chaos of the merger, the orderly orbits of billions of stars are violently randomized. Stars that once traveled on neat, circular paths within a flat plane are now flung onto random, three-dimensional trajectories. The result is no longer a disk but a vast, swelling spheroid, a cloud of stars where motion is turbulent and without a preferred direction of spin. This is the birth of an elliptical galaxy, a structure defined by its lack of structure. The transformation is not just kinematic, it is also a matter of color and life. The same immense compression that triggered the brilliant starburst also seals the galaxy's fate. That frenzied burst of star formation either consumes the remaining interstellar gas in a final blaze of glory, or powerful shockwaves from the collision and from supernova explosions violently expel it into intergalactic space. With its primary fuel supply gone, the galaxy can no longer form new, hot, blue stars. The only stars left are the old, aging population, which steadily cool and redden over time. This is why elliptical galaxies glow with a distinct, reddish-gold hue, a quiet and solemn color that speaks of a past era of furious creativity. This profound metamorphosis solves a long-standing cosmic puzzle, the Hubble sequence. The elegant tuning fork diagram, which classifies spirals and ellipticals as separate branches, is not a gallery of distinct species. It is a family album capturing different stages in a galactic life cycle. A majestic, star-forming spiral and a quiet, red elliptical are not inherently different kinds of objects. They are the same fundamental entity seen before and after a defining, cataclysmic event. The spiral is the vibrant, youthful city, bustling with construction. The elliptical is the same city, centuries later, its grand monument still standing but its factories silent, its growth complete. This cycle of merging and transformation has been the primary sculptor of the galactic population we observe across the universe, a relentless process of construction and reinvention that has built the cosmic architecture we see today. Drifting through the dense neighborhoods of galaxy clusters are cosmic phantoms, the ultra-diffuse galaxies. These are spectral giants, spanning distances comparable to our entire Milky Way, yet they hold only a tiny fraction of its stars, making them almost transparent against the blackness of space. Their existence poses a profound puzzle. How can an object so large contain so little, its starlight stretched into a faint, ethereal glow? The answer may lie in the very violence of their surroundings. One compelling theory suggests these are the lingering ghosts of past collisions. Imagine a small but normal, dwarf galaxy venturing too close to a colossal neighbor within a bustling galaxy cluster. The immense tidal forces of the giant galaxy, combined with the harsh pressure from the superheated gas that fills the cluster, act like a cosmic sandblaster. This violent environment can strip away the dwarf's dark matter halo and its reservoir of star-forming gas, leaving behind only a skeleton of ancient stars, a galaxy that has been hollowed out. This ghostly remnant continues to orbit, a permanent record of a traumatic encounter. But there is another, equally fascinating possibility. Perhaps some ultra-diffuse galaxies were stillborn. In this scenario, internal processes are to blame. Intense radiation and powerful stellar winds from the galaxy's first massive stars could have blown its gas away before it had a chance to form the vast majority of its stellar population. It was a galactic engine that stalled almost immediately after starting, leaving behind a faint, failed structure. The presence of these phantoms forces us to rewrite the story of galaxy formation. They reveal that the outcomes of cosmic evolution are far more diverse than we once believed. By studying their faint light, astronomers can peer into the most extreme environments of the universe, using these fragile ghosts as probes to understand the invisible forces and violent histories that sculpt entire galactic communities. Galaxy clusters are the ultimate cosmic arenas, where the rules of construction and destruction are written on the grandest possible scale. These are not mere collections of islands. They are sprawling, dynamic metropolises, the largest structures gravity has ever bound together. Within these dense cities of galaxies, collisions are not rare events. They are the dominant process, the constant background hum of cosmic life. The interactions here vary dramatically. Some are fast, high-speed flybys, where galaxies streak past each other like ships in the night, their gravitational fields briefly intertwining before they continue on their way. These encounters can still leave lasting scars, distorting spiral arms and triggering waves of new star formation. But other encounters are far more intimate and disruptive. When a galaxy moves through the dense, superheated gas that fills the space between galaxies in a cluster, it can experience a phenomenon known as ram pressure stripping. Imagine a spider web drenched in morning dew. If you swing your hand through it, the dew droplets are torn away. In a similar way, the immense pressure of this intergalactic medium acts like a powerful wind, physically stripping a galaxy of its own cold gas, the very raw material needed to form new stars. This process can effectively suffocate a galaxy, leaving it to age passively, its blue spiral arms fading to a quiet gold. At the very heart of these clusters sit the true titans, the brightest cluster galaxies. These colossal elliptical galaxies did not form in isolation. They are the products of relentless galactic cannibalism, growing to immense sizes by consuming any smaller galaxy that ventures too close on a cosmic timescale. Their growth is a form of extreme accretion, a steady diet that has built the most massive single galaxies in the entire universe. The collisions within a cluster are not limited to the galaxies themselves. The clusters contain immense reservoirs of multimillion-degree gas, so hot it glows not in visible light but in powerful X-rays. When two galaxy clusters themselves begin to merge, these vast oceans of hot gas slam into one another. The collision releases more energy than all the stars in all the galaxies within them combined, creating spectacular shock fronts that ripple through the intergalactic medium. These are the largest shock waves known to exist, visible only to X-ray telescopes, and they heat the gas to even more extreme temperatures. In these dense, violent environments, we see the most extreme forms of cosmic architecture at work. The fate of a galaxy is no longer determined solely by its initial conditions, but by the bustling, often hazardous neighborhood it calls home. The quiet, majestic spiral we might see in an isolated part of the sky would be stripped, shredded, or consumed if it were placed in the heart of a bustling cluster. This reveals a profound truth about our universe. The final form of a galaxy is not just about what it is made of, but where it lives. A galaxy can be robbed of its future without a single direct collision. This is the silent, pervasive effect of ram pressure stripping, a process where a galaxy's environment becomes its greatest adversary. Picture a vast spiral galaxy, rich with cold, dense gas clouds, as it plunges through the superheated plasma that fills the space between galaxies in a massive cluster. This plasma, known as the intracluster medium, is incredibly thin by Earth standards, but the galaxy is moving through it at millions of miles per hour. The resulting sensation is like sticking your hand out of a car window at high speed, feeling the push of the air. For the galaxy, this is not a gentle breeze but a hurricane-force gale. This is ram pressure, a powerful wind that acts directly on the galaxy's interstellar gas. The galaxy's stars and its invisible dark matter halo pass through this wind unaffected, as they do not collide with the particles. But the gas, the very raw material for new stars, is vulnerable. The relentless pressure can become so immense that it overcomes the galaxy's own gravity, the force that holds its gas clouds in place. It then does the unthinkable. It physically blows that star-forming fuel right out of the galaxy, flinging it into the void. We can see the forensic evidence of this cosmic robbery in stunning detail. Some galaxies exhibit long, trailing tails of gas that stream behind them like celestial comets. Others, known as jellyfish galaxies, display wispy tentacles of gas being forcibly pulled away, their structures distorted by their motion through the hostile medium. This violent stripping has a profound consequence. It quenches the galaxy. The vibrant blue spiral, once bustling with the birth of new, massive stars, is left gas-poor and passive. Its remaining population of stars will age and redden, transforming the galaxy into a quiet, red and dead system. This reveals a critical truth about galactic evolution. A galaxy's destiny is not written solely by its internal dynamics or its direct mergers. It is also dictated by the neighborhood it inhabits, a reminder that sometimes the greatest forces shaping the cosmos are the silent, invisible currents flowing through the deepest voids. We cannot watch a single galactic collision unfold in real time, so we build digital universes instead. To understand these billion-year-long dances, astronomers turn to some of the most powerful supercomputers on Earth. These machines run what are known as N-body simulations, vast digital experiments that model the cosmos. In these simulations, a galaxy is not a single object, but a colossal collection of millions or even billions of individual particles. Each particle represents a parcel of dark matter, a cluster of stars, or a cloud of interstellar gas, all interacting solely through the force of gravity. The computer calculates the gravitational pull between every single particle and every other particle at each moment in time, advancing the simulation forward in a series of tiny steps. Watching one of these simulations play out is like watching a cosmic ballet in fast forward. You witness two blobs of light representing spiral galaxies slowly approaching each other. Their mutual gravity stretches them, pulling out long tidal tails of particles. They swing past each other, then fall back together in a final, violent merger, their structures erased as they swell into a single, smooth, elliptical galaxy. This digital recreation is breathtakingly accurate, but it starts with gravity alone. To make these virtual galaxies feel real, scientists must add layers of complexity. They incorporate the physics of fluid dynamics to simulate how colliding gas clouds compress, heat up, and trigger the formation of new stars. They program in the effects of supernova explosions, which can blast gas out of the galaxy, halting star formation and altering its evolution. This intricate feedback between stars and gas is what turns a simple gravitational model into a living, breathing virtual galaxy. Major projects like the Illustris TNG and EAGLE simulations have achieved something remarkable. They begin with conditions resembling the early universe and let the simulation run for billions of virtual years. The result is not a single galaxy, but an entire virtual cosmos, populated with a diverse menagerie of spirals and ellipticals that look statistically identical to the real universe we observe through our telescopes. This success is a powerful validation of our core theory, that the large-scale structure of the cosmos is built hierarchically through the relentless merging of smaller structures into larger ones. These simulations are more than just movies, they are predictive tools. A scientist can run a virtual experiment, changing one variable at a time. What happens if the collision is a direct head-on impact versus a glancing blow? How does the presence of more dark matter change the final shape of the merger remnant? By tweaking the initial conditions, we can test our theories against the universe itself, using these digital laboratories to decode the hidden physics that has sculpted every galaxy we see in the night sky. Gravity may be the master architect, but it does not work alone. A far more subtle force is woven into the fabric of interstellar space, a force that guides the flow of matter in ways we are only beginning to understand. This is the influence of magnetic fields. Threaded throughout the gas between the stars are these invisible lines of force, incredibly weak by earthly standards, yet spanning tens of thousands of light years. During a collision, this delicate magnetic tapestry is caught in the turmoil. The violent, turbulent motions of the merging gas act like a cosmic dynamo, stretching, twisting, and amplifying these magnetic fields until they become a significant player in the drama. They begin to exert a gentle pressure of their own, influencing how giant clouds of gas collapse and fragment. This magnetic guidance can regulate the birth of stars, preventing some clouds from collapsing too quickly while channeling streams of gas on long journeys toward the galactic center. There, this organized flow of material can fall onto the waiting supermassive black hole, feeding it and potentially awakening a brilliant quasar. We can actually see the ghostly outline of these magnetic architectures. Radio telescopes detect a specific kind of radiation called synchrotron emission. This is the light given off by electrons traveling at nearly the speed of light as they spiral around these magnetic field lines. In the aftermath of a collision, these emissions trace out the intricate structure of shock fronts and the vast, sweeping curves of tidal tails, painting a picture of invisible forces at work. For scientists building simulations of the cosmos, this adds a profound layer of complexity. It is no longer enough to calculate only the pull of gravity and the flow of gas. Now, they must incorporate the intricate physics of magnetohydrodynamics, the complex dance between magnetic fields and ionized plasma. This reminds us that the cosmic architect employs a full toolbox of physical forces. While gravity draws the grand blueprints, magnetism provides the delicate brushstrokes that define the final, magnificent details of the universe's great structures. Our own galaxy is not an isolated island, but a ship on a long set course. In approximately 4.5 billion years, the Milky Way will begin its final, defining merger with the Andromeda galaxy. This is not a possibility, but a certainty confirmed by the precise tracking of the Hubble Space Telescope. Andromeda is racing toward us at about 250,000 miles per hour, a silent, unstoppable charge across the cosmic void. What will this cosmic event look like from a future Earth? The first changes will be subtle. Over millions of years, the Andromeda galaxy will swell in our night sky, transforming from a faint, fuzzy smudge into a magnificent, structured spiral that dominates the heavens. As the galaxies draw nearer, their mutual gravity will begin to warp and distort their familiar shapes, pulling long, brilliant streamers of stars from their outer disks. The two spiral structures will be stretched and pulled apart, their beautiful symmetry lost to the gravitational turmoil. The galaxies will not collide head-on in a single, cataclysmic moment. Instead, they will perform a gravitational dance, swinging past each other in a close encounter that will last for hundreds of millions of years. During this first pass, the cores of both galaxies will likely miss each other, but their outer stellar populations will be flung into colossal, interwoven tidal tails, creating a spectacle of unparalleled grandeur. After this initial graceful swing, gravity will pull them back together for a final, slower merger. Over another billion years, they will settle into a new, stable structure, a vast, smooth, elliptical galaxy that astronomers have playfully named Milky. This new galaxy will be a hybrid, a fusion of the hundreds of billions of stars from both the Milky Way and Andromeda. What does this mean for our solar system? The vacuum of space is so vast that the probability of any two stars actually colliding is vanishingly small. Our Sun and its planets will almost certainly be physically safe, but they will likely be flung onto a new, radically different orbit, perhaps carried far out into the galactic halo of this new entity. The familiar band of the Milky Way will be gone forever, replaced by a diffuse, golden glow of ancient stars. This future collision provides a profound sense of perspective. It connects the grand, impersonal cosmic processes we observe in distant galaxies directly to our own home. It shows us that our galaxy is not a permanent monument, but a temporary structure in an ever-evolving universe, with its own life story that includes a dramatic, transformative finale. The fate of our own solar system is a deeply personal question within this cosmic upheaval. Amidst the swirling chaos of billions of stars, will our tiny planetary oasis survive? The vast emptiness of space is our greatest protector. The average distance between stars is so immense that a direct collision between our Sun and another star is a statistical near impossibility. The real changes will be more subtle yet profound. The gravitational tides of the merger could act like a cosmic slingshot, flinging our entire solar system from its familiar circular path into a much wider, more elliptical orbit within the new galactic core. In an even more extreme scenario, we could be completely ejected, cast out from the galaxy entirely to drift through the cold, intergalactic void as a rogue solar system. A more immediate concern arises not from gravity but from radiation. The collision-triggered starbursts will ignite countless supernovae in relatively close proximity. The intense radiation from these stellar explosions could potentially erode or alter the atmospheres of planets, a hazard for any life that might exist. Yet, through all this, the solar system itself will likely remain physically intact. This resilience highlights a beautiful cosmic hierarchy. While the grand architecture of galaxies is constantly torn down and rebuilt, the smaller, intricate structures of planetary systems often endure, stable islands within the swirling cosmic storm. For centuries, the universe beyond our Milky Way appeared serene and orderly. Astronomers saw these distant island universes as solitary beacons, each evolving in splendid isolation. This peaceful view was permanently shattered by a single, revolutionary catalogue. In 1966, astronomer Holton Arp published his Atlas of Peculiar Galaxies, a gallery of cosmic oddities that defied all conventional classification. Here were galaxies with long, sweeping tails, others connected by delicate bridges of starlight, and some so warped and distorted they seemed to be caught in a cosmic whirlwind. These were not serene islands, they were dynamic systems caught in the act of violent interaction. Initially, many of these bizarre structures were mistaken for single, chaotic objects. How could one galaxy produce such spectacular, asymmetric features? The answer slowly emerged as telescopes and theoretical models improved. Each peculiar shape was not one object, but two or more galaxies captured in a fleeting moment of gravitational interplay. Arp's atlas provided the crucial visual evidence that galaxies could collide, merge, and reshape one another. This was a profound paradigm shift in how we understood the cosmos. The universe was no longer a static collection of islands, but a dynamic, ever-changing arena where galaxies continually interact and evolve. This historical pivot reminds us that our cosmic perspective is never final. It is a story constantly being rewritten by the evidence we gather, revealing a universe that is far more active and interconnected than we ever dreamed. A galactic collision can create a furnace so brilliant its true power remains completely hidden from our eyes. The most energetic events in the universe often play out behind thick, swirling curtains of cosmic dust. This is the realm of luminous infrared galaxies, celestial powerhouses whose ferocious light is absorbed and transformed. these colossal objects and their even more extreme cousins known as ultra-luminous infrared galaxies shine not in visible light but in the warm glow of infrared heat. Their immense energy is almost always the direct result of a violent merger. When two galaxies combine, their gravitational dance funnels enormous reservoirs of gas and dust toward the shared center. This concentrated fuel ignites a firestorm on two fronts. It triggers a frenzied starburst, birthing millions of stars at a ferocious rate, while also feeding the central supermassive black hole, driving it to a state of intense activity. The ultraviolet and visible light from these brilliant newborn stars and the glowing accretion disk around the black hole is immediately absorbed by the thick shroud of dust. The dust heats up until it glows, re-radiating all that captured energy at longer, infrared wavelengths. It is a cosmic sleight of hand, where the most visible signs of creation are converted into an invisible thermal signature. We have a prime example relatively close to home. The galaxy known as ARP 220 is a brilliant nearby luminous infrared galaxy, the product of two spirals crashing together. Studying it is like having a front-row seat to a phenomenon that was the dominant mode of galaxy building in the early, crowded universe. These dusty powerhouses reveal a critical phase of cosmic evolution, a hidden, explosive chapter where the universe constructed its most massive galaxies behind a veil of its own making. A cosmic firestorm contains the seeds of its own destruction. Within the brilliant chaos of a galactic collision, a self-regulating mechanism emerges to prevent runaway growth. This is the vital principle of feedback, where the very processes of creation unleash forces that ultimately limit it. When a starburst ignites, it forges countless massive stars. These stellar giants live fast and die young, ending their short lives in cataclysmic supernova explosions. Each detonation is a titanic release of energy, flooding the surrounding space with shockwaves and radiation. Simultaneously, at the galactic core, the merger-funneled gas is feasted upon by the central supermassive black hole. As matter spirals inward, it does not go quietly. This process can power immense jets of particles and drive hurricane-force winds, all moving at nearly the speed of light. These outflows from the black hole inject a staggering amount of energy back into the galaxy's reservoir of gas. This is the feedback loop in action, the collective effect of countless supernovae and the ferocious output from the black hole heats the surrounding interstellar gas to immense temperatures. Imagine trying to build a snowman next to a roaring bonfire. The snow simply melts away. In the same way, this injected energy prevents the giant clouds of cold gas from collapsing further under their own gravity. The very fuel for new stars is heated and dispersed, dramatically slowing or even halting the star formation frenzy that the collision initially sparked. In the most extreme cases, this feedback can generate galactic winds so powerful they blow the gas clean out of the galaxy itself. Vast rivers of material are ejected into intergalactic space, a permanent loss of the galaxy's future building blocks. This process answers a fundamental question about our universe. Why are galaxies not vastly larger and more luminous than they are? Why is so much of a galaxy's original gas left unused, never converted into stars? Feedback is the cosmic thermostat that prevents the system from overheating and burning through all its fuel in one single, brilliant flash. It ensures that star formation is a long, regulated process rather than a brief, all-consuming inferno. Without this balancing act, galaxies would have exhausted their gas billions of years ago, leaving the universe dark and sterile long before planets like ours could form. This delicate dance between creation and limitation is not just a theoretical idea. It is the essential ingredient that allows our digital models of the cosmos to finally mirror the quiet, mature galaxies we actually see in the night sky. This color shift in the cosmos reveals a universe in constant renovation. In the 1970s, astronomers Beatrice Tinsley and later the team of Harvey Butcher and Augustus-Oemler noticed something peculiar when they looked deep into space and therefore far back in time. They found that younger galaxy clusters, those billions of light-years away, were not the serene, golden cities we see nearby. Instead, they were bustling with blue, star-forming spiral galaxies. Compare this to the clusters in our modern, local universe, which are dominated by the quiet, red glow of elliptical galaxies. This profound difference, now called the Butcher-Oemler Effect, is like finding a cosmic fossil record. It provides direct, observational proof that the population of galaxies has evolved dramatically over the eons. The vibrant, blue spirals of the past were systematically transformed into the red, passive ellipticals we see today. But what cosmic mechanism could account for this wholesale change? The answer lies in the hazardous life within a dense cluster. These crowded environments act as galactic transformation factories. As a spiral galaxy falls into a cluster, it encounters a hostile environment. The relentless ram pressure of the superheated intergalactic gas can strip it of its star-forming fuel, suffocating it slowly. At the same time, the high density of galaxies makes close encounters and mergers a frequent event, violently scrambling elegant spirals into smooth ellipticals. This is not a gentle aging process, it is a forced metamorphosis driven by the neighborhood. The Butcher-Oemler Effect is one of the most powerful pieces of evidence we have that the universe's architectural style is not fixed. The cosmic landscape was once a vibrant, blue canvas of construction, which has, over billions of years, been gradually painted over with the solemn gold of completion, all thanks to the relentless interactions in its densest urban centers. The elegant symmetry of a spiral galaxy is far more fragile than it appears. A single, gentle gravitational nudge can reshape its entire internal architecture, forging the very heart of the stellar city. When a smaller satellite galaxy passes nearby, its gravity sends ripples through the larger spiral disk. These ripples act like a cosmic stirring spoon, mixing up the orderly orbits of billions of stars. This gravitational perturbation drives a remarkable migration, pushing vast streams of gas and stars from the outer disk inward toward the galactic center. As this material piles up, the central region begins to swell, puffing up into a dense, spherical structure astronomers call a classical bulge. This is how a galaxy grows a heart, not through internal processes alone, but from the external influence of a cosmic companion. The same gravitational encounter can warp the disk in another profound way. The orderly circular motion of the disk is disrupted, causing it to lose its perfect symmetry and buckle. From this instability, a new structure emerges, a massive bar that cuts straight through the galactic center, connecting the spiral arms. This bar is not a static sculpture. It is a dynamic engine, a cosmic conveyor belt. Stars and gas clouds caught within its gravitational influence do not orbit the center in perfect circles. Instead, they follow elongated paths that channel material from the outer disk directly inward along the bar's lanes. This relentless funneling action has dramatic consequences. It can deliver vast quantities of cold gas to the innermost regions, compressing it and igniting a furious burst of new star formation right at the galactic core. This same river of fuel can also flow directly to the waiting supermassive black hole, potentially awakening it from its slumber and powering brilliant activity. The presence and prominence of these features in a galaxy like our own Milky Way are therefore more than just aesthetic details. They are a living fossil record, a permanent imprint of past disturbances. A large classical bulge and a strong central bar are signatures of a dynamic life, revealing that the galaxy has experienced significant gravitational encounters throughout its long history. They are the architectural legacies of ancient collisions, the enduring marks of a cosmos that is anything but static. The most dramatic evidence of a galactic collision fades in a cosmic blink. Those beautiful tidal tails and warped disks, the clear signs of a recent encounter, dissolve away after just a few 100 million years, a mere moment in a galaxy's multi-billion-year life. So how do we find the ancient relics, the galaxies that were forged in a major merger so long ago that all the obvious scars have healed? Astronomers become cosmic detectives, searching for subtle, lasting clues that betray a violent past. One of the most telling signs is a profound internal disorder. By using spectroscopy to measure the motion of stars, scientists can read a galaxy's kinematic fingerprint. In a spiral galaxy, most stars travel in an orderly, rotating disk. But in an elliptical galaxy born from a merger, the stellar orbits are completely randomized, with stars moving every which way in a turbulent, swollen cloud. This chaotic motion is a permanent legacy of the gravitational turmoil that erased the original disks. Another clue lies in the galactic core itself. Sometimes a galaxy may harbor not one, but two distinct nuclei at its center, the stubborn, slowly merging hearts of the original black holes from the two progenitor galaxies. Even after they coalesce, the aftermath can leave the new core noticeably offset from the galaxy's true gravitational center, a permanent wobble from the colossal impact. The stellar population itself holds a chemical diary of that ancient event. The stars in a galaxy act like a fossil record of its star formation history. A galaxy that formed primarily through a sudden, violent merger will show a very distinct signature. Its stars will be predominantly old, with a sharp, intense peak in their age distribution, indicating a single, enormous burst of star formation during the collision, followed by a long, quiet period with very few new stars being born. This is the chemical footprint of a starburst that consumed the galaxy's gas and left it quiescent. Perhaps one of the most fascinating clues comes from a galaxy's entourage of globular clusters. These dense, spherical swarms of ancient stars often exist in vast numbers around massive galaxies. A galaxy that is the product of a major merger will frequently possess a huge, rich system of globular clusters, far more than a typical spiral. Why? Because the collision didn't just mix the stars of the two galaxies. It also captured and accumulated the entire collections of globular clusters that once orbited each progenitor. Finding these subtle signatures is not just an academic exercise. It is the key to taking a cosmic census, to understanding how many of the galaxies we see today are the quiet survivors of a dramatic, transformative clash. By identifying these ancient merger remnants, we can finally reconstruct the full history of galactic assembly, piecing together how the great cities of stars were built, collision by collision, across the deep time of the universe. The universe occasionally crafts a structure so perfect it seems almost impossible. Hoag's object is one such celestial marvel, a galaxy that appears as a luminous golden core nestled inside a flawless, brilliant blue ring of stars. It is a cosmic bullseye, a perfect circle hanging in the void. How could gravity alone produce such a symmetrical and beautiful form? The answer appears to lie in a specific, almost surgical type of collision. Astronomers theorize that a smaller galaxy, acting like a cosmic projectile, once passed directly through the center of a larger, normal spiral galaxy. Picture the calm, flat disk of the spiral. The intruder plunges straight through its heart, not colliding with stars, but sending a powerful gravitational shockwave rippling outward through the disk. This is the galactic equivalent of dropping a single pebble into the center of a still pond. The ripple that expands is a density wave, a circle of intense pressure racing through the gas-rich disk. As this wave travels outward, it violently compresses the interstellar gas it encounters. This sudden squeeze pushes the gas past its limit, triggering a cataclysmic burst of star formation in a perfectly circular pattern. The wave essentially constructs its own ring of brilliant, young, blue stars as it moves, while the galaxy's original core, having experienced the gravitational disturbance but remaining largely intact, is left behind as the older yellow heart. This precise bullseye impact is a controlled experiment on a galactic scale. It demonstrates with stunning clarity how a single, well-defined event can directly forge a unique and spectacular shape. The perfect ring of Hoag's object is not a mystery of creation, but a signature of destruction, a lasting monument to the day a smaller galaxy pierced the heart of another and left behind a halo of new light. The same cosmic collisions that build galaxies also illuminated the universe's greatest dawn. For hundreds of millions of years after the Big Bang, the cosmos was a featureless, silent fog. A thick shroud of neutral hydrogen gas filled all of space, absorbing light and keeping the universe in a profound and endless darkness. This was the cosmic Dark Ages. The transformation that ended this era, the epoch of reionization, required a colossal release of energy to burn away that primordial fog. The key was a specific type of light, ultraviolet radiation, which has enough energy to strip electrons from hydrogen atoms, turning them from a light-absorbing mist into a transparent, ionized plasma. But what cosmic engine could possibly produce enough ultraviolet light to clear a universe? The answer lies in the frantic construction sites of the early cosmos. In that younger, denser universe, galactic collisions were not rare events. They were the standard mode of assembly. As small, primordial galaxies constantly merged, their violent encounters triggered ferocious starbursts on a scale we rarely see today. These were not the gentle births of sun-like stars. These collisions forged immense numbers of colossal, short-lived stellar giants. These massive stars burned fiercely and died young, and in their brief lives, they flooded the cosmos with the very ultraviolet radiation needed to ionize the hydrogen fog. Each merger acted as a powerful beacon, its intense starlight carving out ever-growing transparent bubbles in the surrounding darkness. But stars were not the only source of light. The chaotic dynamics of these early mergers efficiently funneled vast amounts of gas toward the centers of galaxies, feeding the first supermassive black holes. This feast of matter awakened these monsters, turning them into brilliant quasars, whose intense beams of energy acted as cosmic blowtorches. Their radiation was so powerful it could travel far through the intergalactic medium, contributing significantly to the clearing of the universal haze. This collaborative effort, driven by the relentless churn of galactic collisions, fundamentally changed the nature of the cosmos. The opaque fog lifted, and for the first time, light could travel freely across the universe. The grand architectural process that built the galaxies also flipped the cosmic switch, turning on the lights for everything that was to come. The final stages of a galactic merger reveal one of the universe's most energetic duos. When two gas-rich spiral galaxies collide, their combined gravitational dance funnels immense amounts of interstellar gas directly toward their respective centers. This cosmic windfall can simultaneously ignite the supermassive black holes at the heart of both galaxies, turning them into brilliant, active galactic nuclei. The result is a dual AGN system, a pair of fiercely luminous beacons blazing within a single, chaotic merger remnant. Observing this phenomenon is incredibly difficult. From our vantage point millions of light-years away, the two active cores can appear as a single, unresolved point of light. Their angular separation in the sky is minuscule, a tiny fraction of the width of the full moon, demanding the utmost precision from our telescopes. Yet confirming their existence is crucial, as it provides the most direct evidence that galactic collisions are the primary mechanism for feeding and awakening these cosmic monsters. As the two black holes continue their inward spiral, drawn together by dynamical friction, they may eventually orbit so closely that they share a single, bright nucleus of gas and stars. At this point, they are considered a binary AGN, a pair of gravitational titans locked in a final, tight embrace within the heart of their new galactic home. These systems are the ultimate cosmic laboratories for understanding black hole dynamics. They allow us to test our theories of how supermassive black holes shed their orbital energy and spiral inward, a process that culminates in a universe-shaking merger and the emission of powerful gravitational waves. The frequency of these events across the cosmos is a key question in modern astrophysics. How often do these colossal pairs form and ultimately collide? Advanced instruments are now giving us our first clear glimpses. The Chandra X-ray Observatory can peer through the obscuring dust, pinpointing the high-energy signatures of two separate accreting black holes. Meanwhile, radio interferometers using very long baselines, which effectively create a telescope the size of our planet, can achieve the resolution needed to distinguish two distinct cores separated by a mere handful of light years. Each confirmed dual or binary system is a snapshot of a process that began with the slow collision of two entire galaxies, offering a precious window into the final, violent moments before two invisible giants become one. This violent rewriting of a galaxy's architecture has a direct and profound consequence for any potential life within it. The concept of a galactic habitable zone suggests that only certain galactic neighborhoods are conducive to complex life. These are regions far enough from the chaotic, radiation-filled core to avoid frequent sterilization by supernova, yet rich enough in heavy elements to form rocky planets. A galactic collision completely shatters this delicate balance. During the initial starburst phase, the entire galaxy becomes a cosmic battlefield. The furious birth of massive stars is swiftly followed by their explosive deaths, flooding interstellar space with intense radiation. For any world orbiting a star in these regions, the sky would be repeatedly lit by the searing flash of nearby supernova, events capable of stripping away planetary atmospheres and bathing surfaces in lethal radiation. Vast stretches of the galaxy that were once considered safe havens would, for hundreds of millions of years, become uninhabitable. Yet, after the storm passes and the new elliptical galaxy settles into its quiet maturity, a different picture emerges. The chaotic spiral structure is gone, replaced by a more uniform, spherical distribution of stars. The stellar density in the core is lower, and the frenetic pace of star formation and death has ceased. This new, calmer environment could, in theory, create a more diffuse and widespread habitable zone. The risk of a nearby supernova diminishes significantly, potentially opening up more of the galaxy's volume to long-term planetary stability. The very event that made life impossible in one era might, over billion-year timescales, create the stable conditions necessary for it to arise in another. This introduces a breathtaking astrobiological dimension to these cosmic crashes. The probability of life existing in a galaxy may not be a constant. It could be a cycle, periodically reset and altered by these grand architectural events, where the death of one generation of worlds might eventually sow the seeds for the next. The final, silent whisper of a black hole merger is written in the fabric of spacetime itself. When two supermassive black holes, forged in the heart of a galactic collision, complete their final spiral and coalesce, they release a phenomenal burst of energy. This energy does not travel as light, but as a ripple in the very geometry of the cosmos, a gravitational wave. These waves from the largest black holes in the universe are the deepest notes in the cosmic symphony, with frequencies so low that a single oscillation can take years. This presents a unique challenge for detection. Ground-based observatories like LIGO are engineered to catch the high-pitched chirps of smaller, stellar mass black holes merging. They are utterly deaf to the deep, rumbling bass notes produced by their supermassive cousins. To listen for these lowest frequencies, we must go to space. The Future Laser Interferometer Space Antenna, or LISA, is designed for this very purpose. It will consist of 3 spacecraft flying in a vast triangular formation, millions of miles apart, using lasers to measure tiny distortions in the space between them. This floating observatory will act as a colossal ear, tuned to the gravitational wave background of the universe. What will it hear? It will detect the final moments of countless supermassive black hole mergers, events that are otherwise completely dark and invisible to our telescopes. By cataloging these signals, LISA will allow us to take a direct census of these cosmic giants. We will be able to measure how often they merge across cosmic time, providing a powerful, independent test of our entire theory of hierarchical galaxy formation. For centuries, our understanding of the cosmos has come entirely from light, from the electromagnetic signals collected by our eyes and our telescopes. Gravitational wave astronomy offers a completely new sense. It will let us hear the universe's great construction projects reaching their conclusion, adding a profound new dimension to our silent movie of the heavens. Even with our most powerful tools, the cosmic architect still holds its deepest secrets close. We can map the grand outcomes of galactic collisions with stunning accuracy, yet fundamental puzzles remain at the very heart of the physics that governs them. For instance, we do not fully understand why some mergers weave intense, large-scale magnetic fields throughout their new structure, while others leave only a faint, disorganized trace. The invisible forces at play during these encounters are subtle and complex, and the rules that dictate this magnetic amplification are still being written. Another profound uncertainty revolves around the cosmic thermostat of feedback. We know that supernova and black hole winds regulate star formation, but the precise mechanisms that determine their efficiency remain elusive. Why does one collision quench its star formation gently, while another violently expels all of its gas into the void? The answer likely lies in the intricate, chaotic dance of energy on a scale we are only beginning to model. This leads to one of the most stubborn puzzles in astrophysics, the final parsec problem. After a galactic merger brings 2 supermassive black holes to within about 3 light-years of each other, their inward spiral seems to stall. How do these colossal objects shed their final bit of orbital energy to coalesce? Do they require a dense cluster of stars to act as gravitational brakes, or is it a vast disk of gas that provides the final drag? The solution is critical as it determines the rate of the universe's most powerful gravitational wave events. Peering back to the dawn of time presents even greater challenges. The earliest mergers involved pristine gas, unpolluted by heavy elements from previous generations of stars, and dark matter halos with properties we can only theorize. Their evolution is poorly constrained by our deepest observations, leaving the first chapters of galactic construction shrouded in mystery. These are not failures of understanding, but the very frontiers of discovery. Each unsolved question directly drives the development of revolutionary new telescopes and ever more sophisticated supercomputer simulations. Our map of the cosmos is detailed and breathtaking, but the blank spaces still on it remind us that the story of how galaxies are built is an epic still being written, with its most thrilling revelations waiting just beyond the next observation. From the gentle tug that forms a spiral arm to the violent embrace that builds an elliptical giant, we have traced the role of these collisions as the universe's master architects. They are the engine behind the star-forming firestorms, the great feasts for supermassive black holes, and the invisible sculptor of dark matter halos. This grand process links the fate of our own solar system to the largest structures in the cosmos, and even to the potential for life on distant worlds. Our journey of discovery is accelerating, propelled by powerful new telescopes that peer deeper into the past and sophisticated simulations that recreate these cosmic events with breathtaking precision. We are unraveling the history of our own galactic home, piece by piece. The silent dance of the galaxies is the ongoing epic of the universe, and by learning its steps, we come to understand the very framework of existence. If this voyage through cosmic architecture has sparked your curiosity, we would love to hear your thoughts in the comments. For more explorations into the mysteries of space, be sure to subscribe.